The universe is vast beyond anything we can truly comprehend, stretching out in all directions farther than light itself has had time to travel since the beginning of everything. When we look up at the night sky, we're seeing only the tiniest fraction of what exists. A few thousand stars visible to our eyes alone, scattered across the darkness like diamonds on velvet. But beyond what we can see lies an ocean of space so immense that our minds struggle to find the edges of it, a cosmic expanse filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, each star potentially surrounded by worlds we'll never visit, never see, never know existed at all. The universe began, as far as we can tell, approximately 13.8 billion years ago, emerging from a state of infinite density and temperature that we call the Big Bang. Though it wasn't really an explosion in any conventional sense. It was more like an expansion of space itself, a stretching of the fabric that makes up reality, carrying matter and energy along with it like debris caught in an outward flowing tide. In those first moments, the universe was incredibly hot, so hot that atoms couldn't even form, just a soup of elementary particles, quarks and electrons and photons bouncing frantically through the primordial chaos. Time itself behaved strangely in those early moments, stretched and compressed by the intense conditions, and space expanded faster than the speed of light, not because anything was moving through space that quickly, but because space itself was growing, inflating like a balloon being filled with air. As the universe expanded, it cooled, the way any expanding gas cools, and after about 380,000 years, it had cooled enough for the first atoms to form. Electrons that had been zipping around freely finally slowed down enough to be captured by atomic nuclei, mostly hydrogen and helium, the simplest elements. This moment, called recombination, was crucial because it allowed light to travel freely for the first time. Before this, photons couldn't move far without bumping into free electrons, but once atoms formed, the universe became transparent, and light could stream through the cosmos unimpeded. That ancient light is still traveling through space today, stretched by the expansion of the universe into microwave radiation that fills the entire sky, a faint afterglow of creation that we can detect with sensitive instruments, a whisper from the beginning of time. The early universe was remarkably smooth and uniform, with matter spread almost evenly throughout space, but not perfectly evenly. There were tiny fluctuations, regions where matter was slightly denser than the surrounding space, and these small differences were enough. Gravity, patient and inexorable, began to pull matter together in these denser regions, very slowly at first, creating subtle concentrations that grew over millions of years. Where matter accumulated, it pulled in more matter, and gravitational attraction grew stronger, a process that fed on itself, building structure in the cosmos like frost patterns forming on a winter window. These growing clumps of matter eventually became the seeds of galaxies, vast collections of gas and dust and dark matter that would evolve over billions of years into the spiral and elliptical islands of stars we see scattered through space today. Dark matter, mysterious and invisible, makes up most of the matter in the universe, about 5 times as much as the ordinary matter that forms stars and planets and people. We can't see dark matter directly because it doesn't emit or absorb light, doesn't interact with electromagnetic radiation at all, but we know it's there because we can see its gravitational effects. Galaxies rotate in ways that don't make sense unless there's much more mass present than we can see, and clusters of galaxies are held together by gravitational forces far stronger than the visible matter alone could produce. Dark matter forms a vast cosmic scaffolding, an invisible web throughout the universe, and ordinary matter falls into the gravitational wells created by this dark structure, gathering in filaments and clusters that trace out the hidden architecture of the cosmos. The first stars formed when the universe was only a few 100 million years old, emerging from collapsing clouds of primordial hydrogen and helium. These early stars were different from the sun and stars we see in our night sky today. They were massive, hundreds of times the mass of our sun, burning incredibly hot and bright, shining with a fierce blue-white light that would have been painful to look at directly if anyone had been there to see. These giant stars lived fast and died young, fusing hydrogen into helium in their cores, then helium into heavier elements, carbon and oxygen, and silicon and iron, creating the building blocks for everything else in the universe through nuclear fusion in their blazing hearts. When these massive stars exhausted their fuel, they exploded as supernovae, spectacular detonations that outshone entire galaxies for brief moments, scattering the newly created elements into space where they could be incorporated into the next generation of stars and planets. Our own sun is a later generation star, formed about 4.6 billion years ago from a cloud of gas and dust that contained elements created in earlier stars and dispersed by ancient supernovae. The atoms in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the cores of stars that died long before our solar system even existed. We are, quite literally, made of stardust, assembled from the remnants of stellar explosions, cosmic recycling on the grandest scale imaginable. When we look at the stars, we're looking at our distant relatives, at the furnaces that created the raw materials for everything we know, everything we are. The sun sits in one of the spiral arms of the Milky Way galaxy, about 2/3 of the way out from the galactic center, orbiting around the heart of the galaxy at a speed of roughly 500,000 miles per hour. Even at this tremendous velocity, it takes the sun about 225 million years to complete one orbit around the galaxy, a period sometimes called a galactic year or a cosmic year. The last time the sun was in this same position in its orbit, dinosaurs were just beginning to emerge on Earth, and it will be another 200 million years before the sun returns to this spot again, long after humanity has either spread to the stars or vanished from existence entirely. The Milky Way itself is a barred spiral galaxy, with long arms of stars and gas and dust spiraling out from a central bar-shaped structure. It contains somewhere between 100 billion and 400 billion stars, though the exact number is difficult to determine because dust and gas clouds obscure our view of much of the galaxy, especially toward the center. At the very heart of the Milky Way, hidden behind clouds of interstellar material, lurks a supermassive black hole, an object containing about 4 million times the mass of the sun compressed into a region smaller than our solar system. This black hole, called Sagittarius A star, sits relatively quiet now, not actively feeding on matter, but occasionally a star or gas cloud wanders too close and gets torn apart, swirling down into the black hole's event horizon in a brief flare of X-rays and gamma rays before disappearing forever from the visible universe. Black holes are among the strangest objects in the cosmos, regions of space-time where gravity has become so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. They form when massive stars collapse at the end of their lives, or when matter accumulates and concentrates in galactic centers, growing over billions of years by consuming stars and gas and merging with other black holes. At the center of a black hole, according to our current theories, lies a singularity, a point of infinite density where the known laws of physics break down completely, where space and time become so warped that they cease to have any conventional meaning. We don't really know what happens at the singularity because our equations fail us there, producing infinities and contradictions that suggest we're missing something important about how reality works at the most extreme conditions. Time itself behaves strangely near a black hole. The intense gravitational field warps space-time so severely that time slows down relative to distant observers. If you could somehow watch someone falling toward a black hole's event horizon, you would see them moving slower and slower, their clock ticking more and more gradually until they seem to freeze just at the boundary, never quite crossing it. Their light red-shifted into invisibility. But from the perspective of the person falling in, nothing special would happen at the event horizon itself. They would cross it without noticing any particular boundary, though they would be stretched by tidal forces, pulled longer and thinner as the difference in gravitational pull between their head and feet became extreme, eventually torn apart in a process sometimes called spaghettification, before finally reaching the singularity at the center. The universe contains structure on scales that are difficult to truly grasp. Galaxies cluster together in groups and clusters, bound by their mutual gravitational attraction. Our Milky Way is part of a small collection called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller dwarf galaxies. The Local Group itself is part of the Virgo supercluster, a larger structure containing thousands of galaxies spread across about 100 million light-years of space. And the Virgo supercluster is just one lobe of an even larger structure called Laniakea, which contains about 100,000 galaxies spanning 520 million light-years. These vast structures aren't distributed randomly through space, but form intricate patterns, sheets and filaments, and walls surrounding enormous voids, regions of space that contain very few galaxies, empty bubbles in the cosmic foam. Light travels at exactly 299,792,458 meters per second in a vacuum, a speed that seems impossibly fast by human standards, but is actually quite slow when measured against the vastness of space. Light from the sun takes about 8 minutes to reach Earth, crossing the 93 million miles between us in the time it might take to have breakfast or read a chapter of a book. Light from the next nearest star, Proxima Centauri, takes 4.2 years to reach us, meaning when we look at that star, we're seeing it as it was 4 years ago, not as it is right now. The light we see left that star before we even looked up, crossing the vast emptiness between stars while we went about our daily lives, completely unaware that ancient photons were rushing toward our eyes. When we look at distant objects in the universe, we're looking backward in time, seeing them not as they are now, but as they were when their light began its journey toward us. Look at a galaxy 10 million light-years away, and you see it as it was 10 million years ago, when our ancestors were just beginning to walk upright on Earth. Look at a galaxy a billion light-years away, and you see it as it was a billion years ago, when life on Earth consisted mostly of simple single-celled organisms floating in ancient seas. The most distant objects we can see, the farthest galaxies detected by our most powerful telescopes, show us the universe as it was more than 13 billion years ago, less than a billion. Years after the Big Bang, when the cosmos was young and the first galaxies were just beginning to take shape. We can never see these distant galaxies as they are right now, in the present moment, because their light hasn't had time to reach us yet. By the time it arrives, billions of years from now, humanity will either have evolved into something unrecognizable or long since disappeared. The expansion of the universe means that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This isn't because the galaxies are moving through space, but because space itself is expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. We can measure this expansion by looking at the light from distant galaxies and noticing that it's shifted toward the red end of the spectrum, stretched to longer wavelengths by the expansion of space during the light's journey to us. The farther away a galaxy is, the more its light is redshifted, and by measuring this redshift, we can determine both the galaxy's distance and how fast space is expanding at that distance. For a long time, astronomers assumed that the expansion of the universe was slowing down, gradually decelerating due to the gravitational attraction of all the matter pulling everything back together. But observations made in the late 1990s revealed something unexpected and rather unsettling. The expansion of the universe isn't slowing down at all, but actually speeding up, accelerating as if some mysterious force were pushing galaxies apart. This discovery earned its finders the Nobel Prize and created one of the biggest mysteries in modern physics. We call this mysterious influence dark energy, though we don't really know what it is or where it comes from. It appears to be a property of space itself, a sort of intrinsic energy density that remains constant even as space expands. So as the universe grows, more dark energy appears to fill the new space, and this energy drives the accelerating expansion. Dark energy makes up about 68% of the total energy content of the universe, which means that more than 2/3 of everything is something we don't understand at all, can barely detect, and have no real explanation for. Stars come in many varieties, classified by their temperature and color and size. The hottest stars burn blue or blue-white, with surface temperatures exceeding 30,000 degrees Celsius, while the coolest stars glow red, with surfaces only a few thousand degrees above absolute zero. Our sun falls somewhere in the middle, a yellow dwarf star with a surface temperature of about 5,500 degrees Celsius, neither particularly hot nor particularly cool, neither very large nor very small. The sun is actually quite an average star in most respects, which is perhaps reassuring. It's stable and long-lived, burning its hydrogen fuel steadily and predictably, providing Earth with consistent energy that has allowed life to evolve and flourish over billions of years. Inside the sun, at the core where temperature and pressure reach unimaginable extremes, hydrogen nuclei fuse together to form helium, releasing energy in the process. This nuclear fusion generates the heat and light that radiate from the sun's surface, streaming out into space in all directions. The energy produced in the sun's core doesn't emerge immediately, but takes thousands of years to work its way to the surface, bouncing around inside the sun as photons are absorbed and re-emitted countless times by the dense plasma. By the time that energy finally escapes and begins its 8-minute journey to Earth, it's already incredibly ancient, older than human civilization, older than our species, older than many of the fossil bones we dig up from the ground. Stars spend most of their lives fusing hydrogen into helium, a phase called the main sequence, which can last billions of years for smaller stars like our sun. But eventually, the hydrogen in the core runs out, and the star must change or die. For stars like the sun, the core contracts and heats up, while the outer layers expand, and the star swells into a red giant, growing hundreds of times larger than it was during its main sequence life. In about 5 billion years, our sun will enter this red giant phase, expanding outward until it potentially engulfs the inner planets, including Earth. The oceans will boil away, the atmosphere will be stripped off, and anything left on the surface will be scorched to ash. But this is still billions of years in the future, an unimaginably long time, longer than Earth has existed so far, enough time for entire civilizations to rise and fall countless times, for evolution to transform life into forms we couldn't possibly predict, for humanity to either spread across the galaxy or vanish into extinction long before the sun becomes a threat. After the red giant phase, a star like the sun will shed its outer layers, puffing them off into space in beautiful shells and rings of glowing gas called planetary nebulae, though they have nothing to do with planets. The core that remains, no longer generating energy through fusion, gradually cools and contracts into a white dwarf, an object about the size of Earth but with the mass of the sun, so dense that a teaspoon of its material would weigh several tons. White dwarfs don't generate new energy, but simply radiate away the heat they still contain from their former life as active stars, gradually fading over trillions of years until they become cold, dark black dwarfs, though the universe isn't old enough yet for any black dwarfs to have formed. Every white dwarf in existence is still glowing faintly, cooling down but not yet extinguished, stellar embers scattered through the darkness. More massive stars have more dramatic endings. When a star many times the mass of the sun exhausts its nuclear fuel, it can't settle into a gentle retirement as a white dwarf. Instead, the core collapses catastrophically in a fraction of a second, and the outer layers crash inward, then rebound outward in a supernova explosion so bright it can outshine an entire galaxy. These explosions are among the most energetic events in the universe, releasing more energy in a few seconds than our sun will emit over its entire 10 billion year lifetime. The shockwave from the supernova plows through space, compressing the surrounding gas and dust, sometimes triggering the formation of new stars in the disturbed regions. The heavy elements created in the star's core and in the supernova explosion itself are scattered into space, enriching the interstellar medium with the raw materials for future generations of stars and planets and eventually life. What's left behind after a supernova depends on the mass of the original star's core. If the core is between about 1.4 and 3 times the mass of the Sun, it collapses into a neutron star, an object so dense that protons and electrons are crushed together into neutrons, forming matter unlike anything found naturally on Earth. A neutron star might be only 20 kilometers across, about the size of a city, but it contains more mass than our entire Sun. A teaspoon of neutron star material would weigh about 1 billion tons, more than all the vehicles on Earth combined. Neutron stars can spin incredibly fast, sometimes rotating hundreds of times per second, and if they emit beams of radiation from their magnetic poles, we detect them as pulsars, cosmic lighthouses whose regular flashing was so precise when first discovered that astronomers briefly wondered if they might be signals from alien civilizations. If the collapsing core is more than about 3 times the mass of the Sun, nothing can stop the collapse. Not even neutrons pressed together as tightly as possible can withstand the crushing force of gravity, and the core continues collapsing past the neutron star stage, compressing down to a point of infinite density, forming a stellar mass black hole. These stellar black holes are scattered throughout galaxies, invisible markers of dead stars, detectable only when matter falls into them or when they orbit another star and distort its light and motion. Every black hole removes a bit of matter from the visible universe, hiding it behind an event horizon where we can never see or retrieve it, though the mass still contributes to the gravitational field that affects surrounding space. The universe is filled with different kinds of light, though most of it is invisible to our eyes. We see only a tiny sliver of the electromagnetic spectrum, the narrow band of wavelengths our eyes have evolved to detect what we call visible light. But extending beyond the red end of the visible spectrum are infrared waves, microwaves, and radio waves, with wavelengths longer than visible light, while beyond the violet end lie ultraviolet, X-rays, and gamma rays, with wavelengths shorter than visible light. All of these are just different forms of light, electromagnetic radiation traveling at the speed of light, but carrying different amounts of energy. Radio waves are low energy and can pass through walls and clouds and even our bodies without causing harm, while gamma rays are extremely high energy and can damage DNA and kill cells, though fortunately, Earth's atmosphere blocks most cosmic gamma rays before they reach the surface. Astronomers study the universe across the entire electromagnetic spectrum, using different telescopes and detectors to observe radio waves from cold gas clouds, infrared from warm dust and forming stars, visible light from ordinary stars like our Sun, ultraviolet from hot young stars, X-rays from gas heated to millions of degrees falling into black holes, and gamma rays from the most violent events in the cosmos. Each wavelength reveals different aspects of the universe, showing us structures and processes we could never see if we relied on visible light alone. The sky looks completely different in radio waves or X-rays than it does to our eyes, with bright objects in one wavelength appearing dim or invisible in another, and vice versa. The universe is far stranger and more complex than what we see on a clear night looking up. Space is not empty, though it might seem that way. Between the stars lies the interstellar medium, thin gas and dust that fills the space within galaxies. By Earth standards, this material is incredibly tenuous, less dense than the best vacuum we can create in our laboratories. But in the vast volumes of interstellar space, it adds up to a significant amount of matter. These clouds of gas and dust are where new stars form, collapsing under their own gravity when they become dense enough, fragmenting into clumps that each form a star or system of stars. The dust grains are tiny, typically smaller than smoke particles, made of carbon, silicon, iron, and other elements, often coated with ices of water, ammonia, and methane. These microscopic particles absorb and scatter light, creating the dark patches we see in photographs of galaxies and nebulae, regions where background stars are hidden by intervening dust. The space between galaxies, the intergalactic medium, is even emptier than interstellar space, containing on average only 1 atom per cubic meter, though some of this matter is quite hot, heated to millions of degrees by shock waves and radiation from galaxies and galaxy clusters. This hot gas doesn't glow in visible light but emits X-rays that we can detect with space-based X-ray telescopes. The intergalactic medium contains the majority of normal matter in the universe, more than exists in all the stars and planets and gas clouds within galaxies. But it's spread so thinly that we barely notice it, an invisible ocean through which galaxies swim like islands. Gravity shapes the universe on the largest scales, pulling matter together into stars, stars into galaxies, galaxies into clusters and superclusters. But gravity isn't the only force at work. In the early universe, the strong nuclear force bound quarks together into protons and neutrons, and later held atomic nuclei together against the electromagnetic repulsion of their positive charges. The weak nuclear force governs radioactive decay and plays a crucial role in the nuclear reactions that power stars. Electromagnetism generates light and holds atoms and molecules together, making chemistry possible, making life possible. These four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, govern everything that happens in the universe, from the smallest subatomic interactions to the largest cosmic structures, though we still don't fully understand how they fit together or whether they might be different aspects of some deeper underlying principle. When we try to imagine the size of the universe, our minds struggle with the numbers involved. The observable universe, the part we can see or could theoretically detect, extends about 46 billion light-years in all directions from Earth. This is larger than you might expect from a universe only 13.8 billion years old, because space itself has been expanding during the time that light has been traveling toward us, stretching out the distance between where a photon started its journey and where we are now. The observable universe contains at least 2 trillion galaxies, though the actual number might be higher, and each galaxy contains tens of billions to hundreds of billions of stars. And many of those stars have planets, and who knows what might exist on those planets, what strange forms of life might have evolved in alien environments we can barely imagine. But the observable universe is not the entire universe, just the part we can see. Beyond the cosmic horizon, beyond the distance that light has had time to travel since the Big Bang, lies more universe, perhaps infinitely more, regions of space we can never observe because their light hasn't reached us yet and, due to the accelerating expansion, may never reach us. These distant regions might be similar to our local universe, filled with galaxies and stars and planets, or they might be different in ways we can't predict. We'll never know for certain because they are forever beyond our reach, not because of any technological limitation, but because of the fundamental physics of space-time and cosmic expansion. Some cosmologists speculate that our universe might be just one among many, part of a multiverse where different regions of space or different bubble universes have different physical properties, different values for fundamental constants, perhaps even different numbers of dimensions or different forces. In some of these other universes, if they exist, stars might not form, atoms might not be stable, life might be impossible. We might live in a universe that's suitable for life simply because we couldn't exist in one of the others, a selection effect called the anthropic principle. But these ideas remain highly speculative, perhaps forever beyond our ability to test or confirm philosophy as much as physics, interesting to contemplate, but not yet science in the strict sense of making testable predictions about observable phenomena. Planets form in the disks of gas and dust that surround young stars, material left over from the star's formation. Dust grains collide and stick together, gradually building up into larger and larger objects, pebbles, then boulders, then asteroids, and finally planets. The inner regions of the disk, close to the star where it's hot, tend to form rocky planets because volatile materials like water and methane evaporate and are blown outward by the star's heat and radiation. The outer regions, cold and distant, can retain these ices, allowing larger planets to form, gas giants that gather not only rock and ice, but also vast atmospheres of hydrogen and helium growing to masses hundreds of times that of Earth. Our solar system formed this way, with small rocky planets near the Sun and gas giants farther out, though we now know this isn't the only possible arrangement. Some exoplanets, planets around other stars, include hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun, and super-Earths, rocky planets larger than Earth but smaller than Neptune, a type of planet we don't have in our solar system at all. We've discovered thousands of exoplanets orbiting other stars, worlds of incredible variety, gas giants and ice giants, and rocky planets, worlds that orbit two stars at once in binary systems, planets with years shorter than an Earth day because they orbit so close to their stars, planets thrown out of their systems entirely, rogue worlds drifting through the galaxy in eternal night, not orbiting any star at all. Some of these exoplanets orbit in their star's habitable zone, the region where conditions might allow liquid water to exist on the surface, a prerequisite, as far as we know, for life as we understand it. Whether any of these potentially habitable worlds actually host life remains unknown. We haven't yet developed the technology to detect biosignatures, signs of life, in the atmospheres of distant planets, though future telescopes might be able to do this, analyzing the light filtered through an exoplanet's atmosphere during a transit to look for gases like oxygen and methane that, in combination, might suggest biological activity. Life on Earth emerged relatively quickly in geological terms, appearing within the first billion years after the planet formed, as soon as conditions stabilized enough to permit it. This might suggest that life arises readily whenever conditions are suitable, or it might mean that Earth was extraordinarily lucky and life is rare in the universe. We don't know. We have only one example, one data point, life on Earth, and from a single example, we can't determine whether life is common or incredibly rare. Scientists have searched for signs of life elsewhere in our solar system, looking at Mars, Europa, Enceladus, Titan, worlds that might have liquid water beneath their surfaces or might have had it in the past. So far, we've found nothing conclusive, no fossils, no microbes, no unambiguous signs that life ever existed anywhere beyond Earth. But the search continues, and absence of evidence is not evidence of absence. The question of whether we're alone in the universe has fascinated humanity for centuries. If life is common, if intelligence evolves frequently, then the galaxy should be full of civilizations, some of them millions or billions of years older than us, with technologies we can't even imagine. Where are they? Why haven't we detected any signals, any signs of their existence? This puzzle is called the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked where everybody is during a lunchtime conversation about the possibility of alien life. There are many proposed solutions to the paradox, each unsettling in its own way. Perhaps intelligent life is extremely rare, and we're alone or nearly alone in the galaxy. Perhaps civilizations destroy themselves shortly after developing advanced technology, victims of war or environmental collapse or some other disaster. Perhaps they're out there, but not communicating, remaining silent for reasons of their own. Perhaps they're so different from us that we don't recognize their signals or structures as artificial. Perhaps the galaxy is indeed full of life, but space is so vast and civilizations so far apart that meaningful contact is impossible. Each intelligent species arising, thriving, and vanishing in isolation, never knowing others exist. We've sent our own messages into space, though they are unlikely to be received by anyone. The Voyager spacecraft, launched in the 1970s, carried golden records with sounds and images from Earth, intended as a message to any civilization that might someday encounter these tiny craft drifting through interstellar space. The records include greetings in dozens of languages, music from around the world, natural sounds like thunder and whale songs, and instructions for playing the record encoded in symbols we hope might be universal. Voyager 1 is now in interstellar space, the first human-made object to leave the solar system, traveling at about 38,000 miles per hour relative to the Sun. At this speed, it will take about 40,000 years to pass within about 1.6 light-years of another star, and it will wander the galaxy for millions or billions of years, long after Earth has changed beyond recognition, perhaps long after the sun has died. The voyagers are messages in bottles cast into a cosmic ocean, more symbolic than practical, our way of saying we were here, we existed, we reached out into the darkness even though we had little hope of reaching anyone. The Milky Way and the Andromeda Galaxy are approaching each other, drawn together by their mutual gravitational attraction, and in about 4 billion years, they'll collide. This sounds catastrophic, but galactic collisions are actually quite gentle affairs in some respects. Stars are so small compared to the distances between them that direct collisions between stars are extremely unlikely. Instead, the two galaxies will pass through each other like ghosts, their stars mostly missing each other, though their orbits will be disrupted, and over hundreds of millions of years, the two galaxies will merge, forming a single larger elliptical galaxy. By the time this happens, the Sun will be approaching the end of its main sequence life, swelling toward its red giant phase. Earth, if it still exists, will be a dead world, airless and lifeless, baked by the growing heat of the aging sun. Any humans who might still be around will have had to leave Earth billions of years before the collision, either spreading to other stars in the galaxy or disappearing entirely from the cosmic story. Galaxies grow by consuming smaller galaxies, gradually building up mass through countless mergers and accretions over billions of years. The Milky Way is currently in the process of consuming several small dwarf galaxies, tearing them apart with its gravitational field and incorporating their stars into its own structure. The Sagittarius dwarf elliptical galaxy is being pulled apart right now as it passes through the Milky Way, leaving streams of stars tracing out its former orbit. These stellar streams are fossils of ancient collisions, archaeological evidence of the Milky Way's violent past, reminders that galaxies are not static objects, but dynamic, evolving structures that change continuously over cosmic time. Time is strange at cosmic scales. 1,000,000 years, an incomprehensibly long period from a human perspective, is barely a moment in the life of the universe, less than 100,000th of the age of the cosmos, a blink. Stars evolve over millions and billions of years. Galaxies take hundreds of millions of years to rotate. The universe itself has been evolving for nearly 14 billion years, and it will continue evolving for trillions upon trillions of years into the future, far longer than it has existed so far, through eras we can barely imagine. As stars exhaust their fuel, galaxies merge and separate, and the universe becomes increasingly cold and dark and empty. In the far future, trillions of years from now, star formation will gradually cease as galaxies use up their reserves of hydrogen gas. Without new stars being born to replace those that die, the universe will slowly dim. The longest-lived stars, small red dwarfs that burn their fuel slowly and carefully, might continue shining for 10 trillion years or more, but eventually even these will exhaust their hydrogen and fade. By 100 trillion years in the future, the era of stars will be over, and the universe will enter what cosmologists call the degenerate era, dominated by cold stellar remnants, white dwarfs and neutron stars, and black holes drifting through an increasingly dark and empty cosmos. These remnants will very slowly evaporate through processes we barely understand. Quantum effects that allow particles to escape even from black holes over unimaginably long timescales. And eventually, perhaps after 10 to the power of 100 years or more, even black holes will evaporate completely, leaving a universe containing nothing but diffuse radiation and perhaps a few scattered elementary particles, cold and dark and nearly devoid of structure, entropy approaching its maximum, time stretching forward into an eternity of darkness with nothing left to mark its passage. But this far future is so distant that it's almost meaningless to contemplate. The difference between now and then is greater than the difference between the Big Bang and now. Entire cycles of cosmic evolution will play out, galaxies will collide and merge, stars will be born and die, countless worlds will form and perhaps host life, and the universe we know will be completely transformed long before the final darkness settles in. We live in a special time, cosmically speaking, in the stelliferous era when stars shine brightly and galaxies are full of light and energy. This era will last trillions of years, but it's finite, a temporary phase in the eternal history of the cosmos, and we're fortunate to exist during it, to be able to look up and see stars scattered across the night sky rather than living in a dark future when the heavens are mostly empty. Neutron stars sometimes occur in pairs, locked in tight orbits around each other, spiraling closer together as they lose energy to gravitational waves, ripples in space-time predicted by Einstein's general theory of relativity and first detected directly in 2015. When two neutron stars finally merge, they produce a brief but incredibly intense burst of gravitational waves and electromagnetic radiation across the spectrum, from gamma rays to radio waves. The collision also creates heavy elements like gold and platinum through rapid neutron capture, flinging these newly created elements into space where they can eventually be incorporated into planets and mined by future civilizations. The gold in your jewelry, if you wear any, was probably created in a neutron star merger billions of years ago, forged in one of the most violent events the universe can produce, then scattered into space and eventually gathered into the cloud of gas and dust that formed our solar system. Gravitational waves are fascinating because they're so different from light. Light is made of photons, particles, or waves of electromagnetic radiation and can be absorbed or scattered by matter. Gravitational waves are distortions in space-time itself, stretching and squeezing space as they pass through, and they interact so weakly with matter that they pass through planets and stars as if they weren't there at all. This means gravitational waves can bring us information from places and events that are invisible in light, like the immediate aftermath of the Big Bang or the interiors of neutron stars, or the final moments before two black holes merge. We're just beginning to use gravitational wave astronomy, having detected only a few dozen events so far, but this new window on the universe promises to reveal phenomena we couldn't study any other way. The cosmic microwave background, that faint afterglow of the Big Bang, contains subtle patterns imprinted on it when the universe was only 380,000 years old, tiny temperature fluctuations of only a few hundred thousandths of a degree. These fluctuations reflect the density variations in the early universe that eventually grew into the galaxies and large-scale structures we see today. By studying the microwave background in detail, measuring the exact pattern of these fluctuations, cosmologists can determine the age of the universe, the density of matter and dark energy, the geometry of space, and many other fundamental properties of the cosmos with remarkable precision. The microwave background has been mapped by several satellite missions, each producing increasingly detailed pictures of the infant universe, showing us what things looked like less than 1,000,000 years after the beginning of time. A baby photograph of the cosmos, taken when it was 1/4000th of its current age. The geometry of space itself is determined by the total density of matter and energy in the universe. If there's enough density, space curves back on itself in a positive curvature, like the surface of a sphere, and the universe would be finite in size, though without edges or boundaries. If there's too little density, space curves in the opposite direction, a negative curvature like a saddle, and the universe would be infinite and open. If the density is exactly at a critical value, space is flat, extending infinitely in all directions with no curvature at all. Measurements of the cosmic microwave background suggest that our universe is very close to flat, within the margin of error, though we can't be absolutely certain. A flat universe means that if you could travel far enough in one direction, you would never return to your starting point, unlike on the surface of a sphere, where traveling in one direction eventually brings you back where you began. Quantum mechanics, the physics of the very small, seems almost incompatible with general relativity, the physics of the very large, yet both theories have been tested extensively and both make predictions that match observations with extraordinary accuracy. Quantum mechanics describes a world of probabilities and uncertainties where particles can be in multiple states simultaneously until measured, where observation itself affects what's observed. General relativity describes space-time as a smooth, continuous fabric that can be bent and stretched by mass and energy. These two descriptions work wonderfully in their respective domains, but clash when we try to apply them both to the same situation, like the singularity inside a black hole or the first moments of the Big Bang. Physicists have spent decades trying to develop a theory of quantum gravity that would unite these two pillars of modern physics. But so far, no such theory has been confirmed, though several candidates exist, including string theory and loop quantum gravity. The ultimate nature of reality at the smallest scales and highest energies remains mysterious, hidden behind a wall of mathematical complexity and experimental inaccessibility. The vacuum of space is not truly empty, according to quantum field theory. Even in the absence of particles, quantum fields permeate all of space, and these fields fluctuate constantly, creating virtual particles that pop into existence in pairs. A particle and its antiparticle then almost immediately annihilate each other and disappear. These vacuum fluctuations are real in the sense that they have measurable effects, influencing the behavior of atoms and the properties of photons passing through empty space. Near the event horizon of a black hole, these quantum fluctuations can become separated before they annihilate, with one particle falling into the black hole while the other escapes, creating what's called Hawking radiation. This means black holes aren't completely black, but actually emit a faint thermal glow, though the temperature of this radiation is incredibly low, far colder than the cosmic microwave background. So all black holes in the current universe are actually absorbing more radiation than they emit. Only in the far future, when the universe has cooled to near absolute zero, will black holes begin to evaporate through Hawking radiation, a process that would take an unimaginably long time, far longer than the current age of the universe. Cosmic inflation, a period of extraordinarily rapid expansion thought to have occurred in the first tiny fraction of a second after the Big Bang, solves several puzzles about the universe we observe. It explains why the universe is so uniform in different directions, why space appears to be flat, and where the tiny density fluctuations that seeded galaxy formation came from. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in less than 10 to the power of negative 32 seconds, doubling in size every 10 to the power of negative 38 seconds or so. This expansion was driven by a hypothetical field called the inflaton field, which had a special property. It created a kind of anti-gravity effect that pushed space apart. When the inflaton field decayed, its energy converted into ordinary matter and radiation, reheating the universe and beginning the more sedate expansion we observe today. The quantum fluctuations in the inflaton field during inflation were stretched to cosmic scales by the expansion, creating the pattern of density variations we see in the cosmic microwave background and ultimately the distribution of galaxies throughout the universe. Ancient cultures saw patterns in the stars and created stories to explain them, constellations representing heroes and animals and gods, myths passed down through generations. These patterns are illusions of perspective, two-dimensional projections of stars that lie at vastly different distances from Earth. The stars in a constellation typically have no physical connection to each other. They're not near each other in space. They just happen to lie along similar lines of sight from our viewpoint. If we could view the constellations from a different location in the galaxy, they would look completely different, the familiar patterns unrecognizable. The constellations slowly change shape even from Earth's perspective as stars move through space over thousands of years, their proper motions gradually distorting the patterns our ancestors knew. In 50,000 years, the Big Dipper will look quite different, its handle bent at a different angle, though human history is too short for anyone to have witnessed these changes directly. Stars themselves are moving through the galaxy at various speeds and in various directions, orbiting the galactic center, but also moving up and down through the galactic disk and drifting sideways relative to each other. Our sun moves through space at about 200 kilometers per second relative to the local standard of rest, the average motion of stars in our neighborhood. Some stars are moving even faster, traveling at hundreds of kilometers per second, sometimes fast enough to escape the galaxy entirely. These hypervelocity stars were likely accelerated by close encounters with the supermassive black hole at the galactic center, or by the explosion of a companion star in a supernova. They're being flung out of the Milky Way into intergalactic space where they'll wander forever, isolated islands of light in the void between galaxies, perhaps with planets still orbiting them, worlds whose night skies show no nearby stars at all, only distant galaxies scattered across the darkness. Quasars, among the most luminous objects in the universe, are supermassive black holes actively feeding on matter, surrounded by swirling accretion disks of gas and dust being heated to millions of degrees as it spirals inward. The intense radiation from these disks can outshine entire galaxies, making quasars visible across billions of light-years of space. Most quasars we observe are very distant, which means we're seeing them as they were billions of years ago, when the universe was younger and black holes were more actively feeding. Quasars were much more common in the early universe than they are now, suggesting that galaxy formation was a messier, more violent process in the past, with more frequent galaxy mergers and more material falling into central black holes. Today, most supermassive black holes sit quietly at the centers of galaxies, not actively feeding, though occasionally a star or gas cloud wanders too close and provides a brief meal, causing a flare of radiation before the black hole settles back into quiescence. The cosmic web, the large-scale structure of the universe, looks remarkably like a neural network or a foam, with galaxies concentrated in filaments and sheets surrounding vast voids. This structure arose naturally from the gravitational growth of small density fluctuations in the early universe, with matter flowing along the paths of steepest gravity, concentrating in certain regions while evacuating others. The voids aren't completely empty, but contain far fewer galaxies than average, and the galaxies they do contain tend to be different from those in denser regions, often smaller and less active. Tracing this cosmic web requires mapping the positions of millions of galaxies across billions of light years, a task that has occupied large astronomical surveys for decades. The resulting maps reveal a universe that's structured on scales far larger than individual galaxies, a cosmic architecture shaped by dark matter and dark energy and billions of years of gravitational evolution. Superclusters, the largest gravitationally bound structures in the universe, contain thousands of galaxies spread across hundreds of millions of light years. But even superclusters are not the largest structures. Galaxies and superclusters are arranged in immense filaments that can stretch for billions of light years, containing tens of thousands of galaxies lined up like beads on a string. These filaments surround and define the voids, creating a sponge-like structure that characterizes the universe on the largest scales we can observe. At scales larger than about 1 billion light-years, the universe starts to look more uniform again, the lumpiness smoothing out into statistical homogeneity, the same average density everywhere. This cosmological principle, that the universe is homogeneous and isotropic on large scales, is a fundamental assumption of modern cosmology, and it appears to be correct based on our observations, though we can only test it within the observable universe, and what lies beyond remains unknown. The speed of light is finite, and this has profound implications. Not only does it mean we see distant objects as they were in the past, but it also means that no information can travel faster than light. No matter can be accelerated to or beyond the speed of light, and causality itself is limited by light speed. Events separated by more than the light travel time between them cannot influence each other. They're causally disconnected outside each other's light cones. This creates a fundamental horizon in the universe, a boundary beyond which we cannot see and from which we can receive no information. As the universe expands and the expansion accelerates, this horizon actually shrinks in some sense, with distant galaxies crossing beyond it, disappearing from our future view, not because they've been destroyed, but because space between us and them is expanding faster than light can travel across it. Billions of years in the future, if dark energy continues to dominate the expansion, the observable universe will shrink, with fewer and fewer galaxies visible from any given point, until eventually only the local cluster remains visible, and everything else has receded beyond the cosmic horizon into eternal invisibility. Cosmic rays are not actually rays, but high-energy particles, mostly protons, that zip through space at nearly the speed of light, carrying enormous amounts of energy. The most energetic cosmic rays carry more energy than anything we can produce in our largest particle accelerators, sometimes as much energy as a baseball traveling at 60 miles per hour, but concentrated in a single subatomic particle. We don't fully understand where the highest energy cosmic rays come from, though they're likely accelerated in extremely violent environments like supernova remnants or the jets from active galactic nuclei. When these particles strike Earth's atmosphere, they create cascades of secondary particles, showers that can contain billions of particles spreading across several square kilometers. Detecting these air showers allows us to study cosmic rays indirectly, learning about processes occurring in the most extreme environments in the universe. The composition of the universe has changed over time. In the beginning, after the Big Bang, there was only hydrogen, helium, and trace amounts of lithium, and a few other light elements produced in the first few minutes as the universe cooled. All the heavier elements, everything in the periodic table from carbon to uranium and beyond, were created later in stars or in stellar explosions or in neutron star mergers. The first stars, made only of hydrogen and helium, were different from stars today, and when they exploded, they scattered heavier elements into space, enriching the gas that would form the next generation of stars. This process of stellar nucleosynthesis and dispersal has continued for billions of years, gradually increasing the fraction of heavy elements in the universe. We call this fraction the metallicity, using the term metal to mean any element heavier than hydrogen and helium, which confuses chemists but makes sense to astronomers. The Sun has about 2% of its mass in metals, while the oldest stars have metallicities less than 1/10,000th of the Sun's, showing how the universe has been chemically enriched over cosmic time. Globular clusters are ancient collections of stars, spherical groupings containing hundreds of thousands to millions of stars packed tightly together, orbiting around galaxies like bees around a hive. The stars in globular clusters are among the oldest in the universe, nearly as old as the universe itself, formed when galaxies were young and still taking shape. The stars in a globular cluster are all about the same age and were born from the same cloud of gas, making them excellent laboratories for studying stellar evolution, because we can observe stars at different stages of their lives all in the same population. The densest parts of globular clusters are so crowded that stars occasionally collide or interact gravitationally, stripping mass from each other or even merging, creating exotic objects like blue stragglers, stars that appear younger than their neighbors because they've been rejuvenated by stealing matter from a companion. Magnetars are neutron stars with extraordinarily strong magnetic fields, trillions of times stronger than Earth's magnetic field, strong enough to distort atoms into elongated shapes and to make the vacuum itself behave strangely. These intense magnetic fields gradually decay, releasing enormous amounts of energy in sudden bursts called starquakes when the neutron star's crust cracks and shifts under the stress of the changing magnetic field. A magnetar flare in our galaxy in 2004 released more energy in 1/10 of a second than the Sun produces in 100,000 years, and the radiation was so intense it measurably affected Earth's upper atmosphere from a distance of 50,000 light-years. Magnetars are rare, with only a few dozen known in our galaxy, but they're among the most extreme objects in the universe, representing matter and energy in configurations we can barely imagine and certainly cannot recreate in any laboratory. Brown dwarfs are failed stars, objects more massive than planets but not massive enough to sustain hydrogen fusion in their cores. They form like stars, collapsing from clouds of gas, but without sufficient mass, they never get hot enough at their cores to ignite fusion. Instead, they glow faintly from the heat of their formation, gradually cooling over billions of years like embers from a fire. The boundary between massive planets and small brown dwarfs is fuzzy, somewhere around 13 times the mass of Jupiter, the minimum needed to fuse deuterium, a heavy form of hydrogen. Brown dwarfs blur the line between stars and planets, and studying them helps us understand how both types of objects form and evolve. Planets can be ejected from their star systems through gravitational interactions with other planets or passing stars, becoming rogue planets that drift through the galaxy untethered to any star. These lonely worlds travel through interstellar space in eternal darkness, their surfaces frozen and lifeless, though some might retain enough internal heat to maintain liquid water beneath thick shells of ice, perhaps even hosting simple life in these hidden oceans, completely independent of starlight. We've discovered a few rogue planets, though they're difficult to detect because they emit very little light and only reveal themselves when they happen to pass between us and a more distant star, briefly magnifying its light through gravitational microlensing. There might be billions of rogue planets in our galaxy, perhaps as many as there are stars, a hidden population of worlds wandering in darkness between the stars. Gravitational lensing occurs when light from a distant object passes near a massive foreground object like a galaxy or cluster of galaxies. The gravity of the foreground object bends the light rays, focusing them like a lens, and from our perspective, this creates distorted, magnified, or multiple images of the background object. Sometimes the alignment is so perfect that the background object appears as a ring of light around the foreground object, called an Einstein ring. Gravitational lensing allows us to study objects too distant or too faint to see otherwise, and it also lets us map the distribution of dark matter in galaxy clusters, because the dark matter's gravity contributes to the lensing effect, even though we can't see the dark matter itself. Some of the most distant galaxies ever detected were found by using galaxy clusters as natural telescopes, their immense gravity magnifying the light from galaxies lying billions of light years behind them. Spiral galaxies like the Milky Way have beautiful arms of stars, gas, and dust spiraling out from a central bulge, but these arms are not solid structures rotating like the blades of a fan. If they were, they would wind up completely after just a few galactic rotations, becoming more and more tightly wound until the spiral pattern disappeared entirely. Instead, spiral arms are density waves, regions where stars and gas clouds bunch up temporarily as they orbit through the galaxy, like cars bunching up in a traffic jam. The stars and gas move through the density wave, slowing down as they enter the arm and speeding up as they leave. But the density wave itself rotates at a different speed than the stars, typically slower. The compression of gas as it enters a spiral arm can trigger star formation, which is why spiral arms appear bright. They're full of young, hot, luminous stars that formed recently in the compressed gas, though these stars will drift out of the spiral arm as they age, eventually becoming part of the background stellar population between the arms. Elliptical galaxies, unlike spirals, are smooth and featureless, shaped like footballs or spheres, with no obvious structure, no spiral arms, no central disk. They contain mostly old stars and very little gas or dust, suggesting that star formation ended long ago in these galaxies, all the available gas having been converted into stars or heated so much that it escaped into intergalactic space. Elliptical galaxies are often found in dense clusters where galaxies interact and merge frequently, and they're thought to form primarily through the merger of spiral galaxies. When two spiral galaxies collide and merge, the resulting disruption destroys the delicate spiral structure, scrambling the orbits of stars and creating an elliptical galaxy with stars moving in all directions rather than in an organized disk. The Hubble constant, which measures the current rate of expansion of the universe, has been a subject of controversy in recent years because different methods of measuring it give slightly different results. Observations of the cosmic microwave background suggest a Hubble constant of about 67 kilometers per second per megaparsec, meaning that for every megaparsec of distance, roughly 3 million light years, the recession velocity increases by 67 kilometers per second. But measurements using nearby stars and supernovae suggest a value closer to 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, might just be due to measurement errors, or it might indicate that our standard model of cosmology is missing something important. Perhaps that dark energy evolves over time, or that there's something else we haven't accounted for affecting the expansion rate. Resolving this tension is one of the major goals of current cosmological research. Pulsars, rotating neutron stars that emit beams of radiation from their magnetic poles, are among the most precise clocks in the universe. Their rotation rates are incredibly stable, sometimes more stable than the best atomic clocks we can build on Earth. Astronomers use networks of pulsars as cosmic metronomes, looking for tiny variations in the arrival times of pulses that might indicate gravitational waves passing through the galaxy. Waves with wavelengths of many light years and periods of years to decades, far too long to detect with the ground-based gravitational wave detectors that discovered merging black holes and neutron stars. These pulsar timing arrays are sensitive to gravitational waves from supermassive black hole mergers, events involving black holes millions or billions of times the mass of the Sun at the centers of merging galaxies. Recent results suggest that these arrays may have detected the first signs of this low-frequency gravitational wave background, a hum filling the universe from countless distant supermassive black hole mergers occurring over billions of years. The universe appears to have a preferred set of physical constants, numbers like the speed of light, the strength of gravity, the mass of the electron, the charge of the proton. These constants determine how matter and energy behave, what kinds of atoms can form, how stars work, whether planets can exist, whether life is possible. If many of these constants were even slightly different, the universe would be drastically changed, perhaps unrecognizable, perhaps unable to support life or even atoms or stars. Why do the constants have the values they do? We don't know. Some physicists argue that there might be a deeper theory that predicts these values, showing they couldn't be anything else. Others suggest the multiverse idea that there are many universes with different constants, and we find ourselves in one suitable for life simply because we couldn't exist in the others. Still, others contend that asking why is meaningless, that these are just brute facts about our universe, parameters we measure, but don't necessarily expect to derive from some deeper principle. Cosmic strings, if they exist, would be defects in space-time itself, incredibly thin but incredibly massive filaments left over from phase transitions in the early universe, similar to cracks that form in ice as water freezes. A cosmic string might be thinner than an atomic nucleus, but stretch across the entire universe with enough mass per unit length that a piece of cosmic string a mile long would outweigh Earth. These exotic objects would produce gravitational effects that might be detectable, and they would generate gravitational waves as they oscillate and decay, though so far we have no confirmed evidence that cosmic strings actually exist. They remain theoretical predictions from certain models of the early universe, fascinating possibilities that might reveal themselves through future observations, or might turn out to be unnecessary complications that nature didn't implement. Wormholes are hypothetical tunnels through space-time, connecting distant regions of the universe or even different universes entirely. Shortcuts that would allow travel between points far apart without crossing the intervening distance. General relativity permits wormholes mathematically, but whether they can actually exist is unclear. Any wormhole that could be traversed would require exotic matter with negative energy density to hold it open, preventing it from collapsing, and we don't know if such matter can exist or be collected in sufficient quantities. Even if wormholes are possible, they might be microscopic and short-lived, quantum fluctuations in the fabric of space-time rather than macroscopic structures you could send a spaceship through. The physics of wormholes involves extreme conditions where quantum effects and gravity both become important, the realm where we need a theory of quantum gravity that we don't yet have. So speculation about wormholes remains largely in the domain of theoretical possibility rather than practical reality. Antimatter is matter's opposite twin, with particles having the same mass as their normal matter counterparts, but opposite electrical charge. An anti-electron, called a positron, has positive charge, while a normal electron has negative charge. When matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy according to Einstein's equation E equals mc squared. This makes antimatter an incredibly efficient energy source in principle, but also incredibly dangerous and difficult to store because it destroys any normal matter container it touches. The universe appears to be made almost entirely of normal matter with very little antimatter, which is Puzzling because the Big Bang should have created matter and antimatter in equal quantities. Something must have created a slight imbalance, a tiny excess of matter over antimatter, perhaps one extra matter particle for every billion matter-antimatter pairs. When the matter and antimatter annihilated, this tiny excess was all that remained, and everything we see around us, all the stars and galaxies, all of Earth, all of us, exists only because of this minuscule initial asymmetry. Understanding why there's more matter than antimatter is one of the great unsolved problems in physics. The cosmic distance ladder is the method astronomers use to measure distances to objects in the universe, a series of techniques that build on each other, each extending our reach farther into space. For nearby objects, we can use parallax, measuring how a star appears to shift against more distant background stars as Earth orbits the Sun, simple trigonometry that works well out to a few thousand light years. For greater distances, we use standard candles, objects whose intrinsic brightness we know, allowing us to determine distance by measuring how bright they appear and comparing that to how bright they actually are. Certain variable stars called cepheids pulse with periods related to their luminosity, and measuring their pulsation period tells us their true brightness. Type Ia, supernovae, explosions of white dwarf stars, are even brighter and can be seen across billions of light years, serving as standard candles for measuring distances to remote galaxies. Each rung of the distance ladder calibrates the next, and errors in nearby measurements propagate outward, which is one reason why determining the Hubble constant precisely is so difficult. Galaxies collide and merge frequently in cosmic terms, though the process is slow by human standards, taking hundreds of millions of years to complete. During a merger, the stars from both galaxies pass through each other, mostly without colliding, but the gas clouds smash together, compressing and heating, triggering intense bursts of star formation that can use up most of the available gas in just a few tens of millions of years. These starburst galaxies can form stars 100 times faster than the Milky Way currently does, creating brilliant blue young stars that make the merging system shine brightly for a brief cosmic moment. Eventually, the starburst ends when the gas is exhausted or heated so much by supernovae and stellar winds that it escapes into intergalactic space, and the merged galaxy settles down, its star formation dying away, perhaps becoming a red and dead elliptical galaxy full of old stars and little else. Tidal forces, differences in gravitational pull across an extended object, can distort and even destroy celestial bodies. The moon raises tides on Earth, pulling more strongly on the side of Earth facing it than on the far side, creating bulges in the ocean and even in the solid crust. Planets or moons can be torn apart by tidal forces if they venture too close to a much more massive body, crossing what's called the Roche limit. Comet Shoemaker-Levy 9 was torn into multiple fragments by Jupiter's tidal forces before crashing into the planet in 1994, an event observed by telescopes around the world and giving us a spectacular demonstration of tidal disruption. Stars can also be tidally disrupted by supermassive black holes, stretched into long streams of gas that spiral into the black hole over weeks or months, producing bright flares of radiation that fade as the stellar debris is consumed. The Oort cloud, a vast spherical shell of icy objects surrounding our solar system at distances from a few thousand to 100,000 astronomical units from the Sun, is the source of long-period comets, those that take hundreds or thousands or even millions of years to complete one orbit. This cloud contains billions or perhaps trillions of cometary nuclei, leftovers from the solar system's formation, scattered to these distant reaches by gravitational interactions with the giant planets. The Oort cloud is so distant that objects within it are only loosely bound to the Sun, and passing stars can perturb their orbits, sometimes sending them falling inward toward the inner solar system where they become visible as spectacular comets, icy visitors from the frozen outer darkness. The Oort cloud has never been directly observed because its objects are too small and too far away to see with current telescopes, but its existence is inferred from the orbits of long-period comets that seem to come from all directions in the sky with no preferred orientation. suggesting they originate from a spherical distribution rather than a flat disk. Lagrange points are special locations in space where the gravitational forces of two large bodies, like the Earth and the Moon or the Earth and the Sun, combine with the centrifugal force of orbital motion to create stable or semi-stable positions where a smaller object can remain with minimal energy expenditure. There are 5 Lagrange points in any two-body system, labeled L1 through L5. The L1 point between Earth and the Sun is where the James Webb Space Telescope orbits, a convenient spot for astronomical observations away from Earth's heat and interference. The L4 and L5 points, located 60 degrees ahead of and behind the smaller body in its orbit, are particularly stable, accumulating dust and asteroids over time. Jupiter has groups of asteroids called Trojans at its L4 and L5 points, thousands of rocky bodies trapped in these gravitational parking spots, co-orbiting with Jupiter but always staying 60 degrees ahead or behind the giant planet. The interstellar medium, the gas and dust between stars, is not uniformly distributed, but varies dramatically in density and temperature. There are cold molecular clouds where temperatures drop to just 10 degrees above absolute zero, and densities reach thousands of particles per cubic centimeter, which is still an excellent vacuum by Earth standards, but dense by interstellar standards. There are warm neutral regions where hydrogen atoms are not ionized, and hot ionized regions where ultraviolet light from young stars has stripped electrons from atoms, creating glowing nebulae. And there are bubbles of extremely hot, very low-density gas heated to millions of degrees by supernovae, expanding through space and sweeping up colder material in their path. Our solar system currently sits in one of these hot bubbles, called the local bubble, a cavity about 1,000 light-years across carved out by ancient supernovae explosions filled with thin hot plasma that emits soft X-rays. The cosmic censorship conjecture, proposed by physicist Roger Penrose, suggests that singularities, points of infinite density where our equations break down, are always hidden inside black holes behind event horizons, never exposed to the external universe as naked singularities. This is reassuring in a way because it means the most extreme breakdowns of physics are concealed from view, unable to affect the rest of the universe in unpredictable ways. But we don't know if cosmic censorship is always true or if there might be ways to create naked singularities under certain extreme conditions. Some solutions to Einstein's equations do permit naked singularities, though they may require special circumstances that never actually occur in nature. The question remains open, one of many regarding the most extreme conditions in the universe that we can barely explore mathematically and certainly cannot test experimentally. Gamma-ray bursts are the brightest explosions in the universe, releasing more energy in a few seconds than the sun will emit over its entire 10 billion-year lifetime. They occur when massive stars collapse into black holes, or when two neutron stars merge, producing narrow beams of intense gamma radiation that sweep across space like the beams from a cosmic lighthouse. If a gamma-ray burst beam happened to point directly at Earth from a nearby source, the radiation could damage or destroy our ozone layer, exposing the surface to harmful ultraviolet light and possibly causing a mass extinction. Fortunately, gamma-ray bursts are rare in any given galaxy, and the nearest known candidate for producing one is hundreds or thousands of light-years away, far enough that we're probably safe from any imminent threat. Though over millions of years, the odds increase that Earth might eventually be in the line of fire from a distant cosmic catastrophe. The Kuiper Belt, a region of the solar system beyond Neptune's orbit, contains thousands of icy bodies, remnants from the solar system's formation that never coalesced into a planet. Pluto is the most famous Kuiper Belt object, though it's now classified as a dwarf planet rather than a full planet. Demoted in 2006 when astronomers decided to clarify the definition of what constitutes a planet, a decision that sparked considerable debate. The Kuiper Belt extends from about 30 to 50 astronomical units from the Sun, and beyond it lies the scattered disk, a more diffuse region of objects with highly elliptical orbits, and beyond that, the Oort cloud. These distant reaches of the solar system are cold and dark, receiving so little sunlight that surfaces are frozen to temperatures only a few dozen degrees above absolute zero. Landscapes of water ice, frozen nitrogen, methane snow, worlds that would be utterly alien and inhospitable to any life as we know it. Panspermia is the idea that life might spread from world to world, or even from star system to star system, carried on meteorites or comets, or perhaps deliberately by advanced civilizations. When a large asteroid or comet hits a planet, it can eject rocks into space, some of which escape the planet's gravity entirely and wander through the solar system or beyond. We've found meteorites on Earth that came from Mars, blasted off the Martian surface by impacts millions of years ago and eventually falling to Earth. If microbes were present in the rocks when they were ejected, and if they could survive the harsh conditions of space, the violent shock of impact, and the intense heat of atmospheric entry, they might seed life on a new world. Whether this has actually happened remains unknown, but the idea is not as far-fetched as it might seem, and some microbes on Earth are surprisingly hardy, capable of surviving extreme radiation, cold, desiccation, and other conditions that would kill most organisms instantly. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the sun at speeds of several hundred kilometers per second. This wind fills the solar system, creating a bubble called the heliosphere that shields us from some of the galactic cosmic rays that would otherwise bombard the inner planets. When the solar wind reaches Earth, it interacts with our magnetic field, funneling particles toward the poles where they collide with atoms in the upper atmosphere, exciting them and causing them to emit light, creating the aurora borealis in the north and aurora australis in the south, shimmering curtains of green and red and purple light dancing across the polar skies. These auroras are beautiful, but they're also a reminder that our planet is not isolated from the sun, but constantly bathed in its influence, connected to our star by invisible threads of magnetism and flowing plasma. Stars are not alone, but often come in pairs or groups, binary systems where two stars orbit each other, triple systems, or even larger associations. Some binaries are so close that they actually touch, with matter flowing from one star to the other, or they might share a common atmosphere, two cores embedded in one vast envelope of gas. These systems evolve in complex ways, very different from single stars, with mass transfer between the components affecting their evolution, sometimes leading to explosive events. If a white dwarf in a binary system accretes enough matter from a companion, it can reach a critical mass where carbon fusion ignites throughout the entire star simultaneously, producing a type Ia supernova that completely destroys the white dwarf in a thermonuclear explosion. These supernovae are remarkably uniform in brightness, which is why they're useful as standard candles for measuring cosmic distances. Voyager 1 and Voyager 2, launched in 1977, are now in interstellar space, having passed beyond the heliopause where the solar wind gives way to the interstellar medium. These spacecraft carry golden records with sounds and images from Earth, time capsules intended for any civilization that might find them billions of years in the future. The Voyagers are now more than 14 billion miles from Earth, so far that radio signals take more than 20 hours to travel one way between the spacecraft and ground stations on Earth. Communication is slow and difficult, and the Voyager's power supplies, radioactive plutonium generators that produce electricity from decay heat, are gradually running down. In a few years, perhaps by the late 2020s, there won't be enough power to run any of the instruments, and the Voyagers will go silent, continuing their journeys through the galaxy as mute artifacts, humanity's farthest-reaching ambassadors to the cosmos. The universe continues expanding, galaxies receding from each other, space itself stretching, carrying everything along with it. The cosmic microwave background grows colder as its photons are stretched to longer wavelengths by the expansion, currently at about 2.7 degrees above absolute zero, cooling slowly as the universe ages. In the far future, this radiation will become even fainter and cooler, eventually undetectable, leaving no trace of the Big Bang visible to any observers that might still exist trillions of years from now in a universe much older and colder and darker than the one we inhabit today. But that future remains distant beyond imagining. And for now, we live in a universe still full of light, still creating stars, still full of possibility and wonder, a cosmos vast beyond comprehension, yet knowable through patient observation and careful thought. We are made of atoms forged in stars. We are the universe's way of knowing itself, conscious matter capable of understanding its own origins and fate, brief sparks of awareness in the immense darkness of space and time, looking outward and inward, wondering and discovering, asking questions that span from the smallest quantum fluctuations to the largest superclusters forming the skeletal structure of the cosmos. It is a curiosity that is woven into our very nature, a drive to understand the environment in which we find ourselves, even when that environment is a vacuum extending for billions of light years. We look for patterns in the chaos, we seek meaning in the mechanics, and in doing so we connect ourselves to the greater whole, acknowledging that we are not separate from the universe, but an integral part of its ongoing story, a way for the cosmos to reflect upon itself in the quiet moments between the stars. The motion of the universe is a complex choreography that happens on scales of time so vast they appear motionless to us. We tend to think of the ground beneath our feet as stable and still, but this is an illusion of perspective. The Earth spins on its axis at 1,000 miles per hour, carrying us from day into night and back again in a rhythm that governs our biological clocks. Simultaneously, the Earth orbits the Sun at 67,000 miles per hour, a journey of nearly 600 million miles every year, traveling through a region of space we have never visited before and will never visit again. The Sun itself orbits the galactic center, bobbing up and down through the galactic plane like a horse on a carousel, and the galaxy moves toward the Andromeda Galaxy, and the entire local group creates a river of matter flowing toward a gravitational anomaly known as the Great Attractor. We are never truly still, never in the same place twice, always traveling at tremendous speeds through the void, protected by the atmosphere and the magnetic field, passengers on a blue vessel sailing through an endless dark ocean. Consider the silence of space, a silence more profound than anything we can experience on Earth. Here, sound is a vibration of air molecules, a pressure wave that travels to our ears, but in the vacuum between worlds, there is no air to carry these waves. Supernovae explode with the power of octillions of nuclear warheads, yet they do so in absolute silence. Galaxies collide and rip each other apart without a whisper. The chaotic storms of Jupiter and the winds of Neptune roar with a fury unknown on Earth, but if you were floating just above their atmospheres in the vacuum, you would hear nothing. This cosmic silence is not empty. It is a heavy, peaceful stillness, a backdrop against which the violence of the universe plays out like a silent film, grand and terrible and beautiful, unfolding in a quietude that has lasted for eons and will last for eons more. Light acts as the messenger of the universe, carrying information across the void, but it is not the only traveler. Neutrinos, ghostly subatomic particles produced in the nuclear fires of the Sun and in the cataclysms of dying stars, stream through the cosmos in numbers that defy comprehension. Trillions of neutrinos pass through your body every second, day and night, passing through the Earth as easily as light passes through glass. They interact so weakly with matter that a neutrino could travel through a block of lead a light year thick without hitting a single atom. These phantom particles carry secrets from the hearts of stars, fleeing the dense core of the Sun in seconds, while photons take thousands of years to work their way to the surface. So, we are constantly bathed in this invisible rain, a silent stream of particles connecting us to the nuclear furnaces burning in the sky, reminding us that space is not truly empty but filled with fields and particles and forces weaving a complex tapestry of reality. The beauty of the cosmos is often found in the nebulae, vast clouds of gas and dust that serve as the nurseries of stars. The Orion Nebula, Visible to the naked eye as a fuzzy patch in the hunter's sword, is a cavern of glowing gas illuminated by the fierce ultraviolet light of massive young stars born within its depths. These stars are carving out a cavity in the cloud, their stellar winds pushing the gas and dust into sculpted pillars and mountains, towering structures light years high. In these dark pillars, hidden from view, new solar systems are condensing, protostars gathering mass from the surrounding cloud, spinning faster and faster until they ignite. The colors of these nebulae tell us their composition: red from glowing hydrogen, green from oxygen, blue from dust reflecting the light of nearby stars. They are the art galleries of the galaxy, transient masterpieces painted in light and shadow that will eventually dissipate, leaving behind clusters of new stars to drift out into the galaxy. Saturn, the jewel of our solar system, offers a different kind of beauty, a study in order and harmony. Its rings are not a solid disk, but a vast field of billions of individual particles, ranging from grains of dust to boulders the size of houses, all orbiting the planet in a flat plane. These particles are made almost entirely of water ice, gleaming white in the sunlight, perhaps the shattered remains of an ancient moon that wandered too close to the planet and was torn apart by tidal forces. The rings are guided by shepherd moons, small satellites whose gravity keeps the ring particles in line, creating sharp edges and narrow gaps, maintaining the delicate structure over millions of years. To float above the rings of Saturn would be to see a landscape of shimmering ice stretching to the horizon, a celestial raceway where countless icy moonlets dance in a silent circular procession around the golden globe of the gas giant. Beyond the planets, beyond the Kuiper Belt, lies the true interstellar void. Here, the sun is just the brightest star in the sky, no longer providing warmth, just a piercing point of light. The distances between stars are so great that the human mind relies on analogies to grasp them. If the sun were a grapefruit in New York City, the nearest star, Proxima Centauri, would be another grapefruit in San Francisco. Between them is nothing but dust and gas and stray atoms, a vacuum so perfect it is better than anything we can create in our best laboratories. Space probes like Voyager and Pioneer are crossing these gulfs, their power sources fading, their transmitters falling silent, drifting into the deep dark. They will wander among the stars forever, carrying the memory of Earth into the infinite, artifacts of a species that looked up and felt the urge to reach out, to touch the void, to send a part of itself into the forever. Gravity is the sculptor of the universe, but it is a patient artist. It works over timescales that make a human life seem like a flicker. It gathers dust into pebbles, pebbles into rocks, rocks into planets. It shapes the spiral arms of galaxies, guiding stars into density waves that ripple through the disk. It binds galaxies into clusters, holding them together against the expansion of the universe. It is the invisible hand that curves space-time, telling matter how to move, while matter tells space-time how to curve. This dance of geometry and mass governs everything from the orbit of the moon to the expansion of the universe itself. We feel it as weight, anchoring us to the Earth, but it is really a connection, a tether, binding us to the planet to the sun, and the sun to the galaxy, a chain of influence that extends to the edge of the observable universe. There are regions of space called voids, immense bubbles of emptiness where galaxies are rare, vast deserts in the cosmic landscape. The Buddha's void is one such region, a sphere of space nearly 300 million light-years across that contains very few galaxies. If the Milky Way were in the center of the Buddha's void, we wouldn't have known other galaxies existed until the invention of powerful telescopes in the 1960s. The night sky would be dark and empty, devoid of the fuzzy patches of light that revealed the true scale of the universe to us. These voids are expanding as matter flows toward the denser filaments of the cosmic web, emptying out the spaces in between, making the universe more porous over time. They are the deep breaths of the cosmos, the silent intervals between the notes of the galactic symphony. The concept of now becomes slippery in the vastness of space. Because light takes time to travel, we never see the universe as it is at this exact moment. We see the moon as it was over a second ago, the sun as it was 8 minutes ago, the stars as they were years or centuries ago. When we look at the Andromeda galaxy, we are seeing it as it was 2.5 million years ago, when early hominids were just beginning to use stone tools in Africa. The universe we perceive is a composite of different pasts, a ghost image constructed from light that has traveled for varying lengths of time. There is no universal now that applies everywhere at once. Time is relative, local, woven into the fabric of space-time that bends and stretches. To look into the sky is to look into a time machine, peeling back the layers of history with every photon that strikes our eyes. Deep in the hearts of galaxies, the density of stars can be astounding. In the solar neighborhood, stars are light years apart, but in a galactic core, they might be light weeks or even light days apart. The night sky on a planet near the Yodiran galactic center would be ablaze with the light of thousands of stars brighter than Sirius, a canopy of brilliance that would cast shadows even at midnight. There, civilizations, if they existed, would not know a dark night. They would live in perpetual twilight, surrounded by a crowded heavens where stellar encounters are common, and the supermassive black hole looms as a dark presence in the gravitational center. It would be a chaotic, energetic environment, very different from the quiet backwater of the spiral arm where our sun resides, a reminder that the universe offers a diversity of environments beyond our experience. The life of a star is a battle between two forces: the crushing weight of its own gravity trying to collapse it inward, and the outward pressure of nuclear fusion trying to blow it apart. For billions of years, these forces remain in balance, a stable equilibrium that allows planets to form and life to evolve. But eventually, gravity always wins. When the fuel runs out, the fire dies, and the star collapses. For the smallest stars, the red dwarfs, this process is incredibly slow. They burn their fuel so efficiently that they can live for trillions of years, longer than the current age of the universe. These small, dim stars will be the last lights left in the cosmos, glowing faintly long after the massive brilliant stars have exploded and the sun-like stars have faded to white dwarfs. They are the endurance runners of the universe, hoarding their energy, destined to watch the galaxy grow dark around them. Water is more common in the universe than we once thought. It exists in the ice of comets, in the rings of Saturn, in the moons of Jupiter and Enceladus, beneath the dusty surface of Mars. We detect water vapor in the atmospheres of hot exoplanets and in the dense clouds where stars are forming. Oxygen and hydrogen, the first and third most abundant elements in the universe, love to bond together. The universe is, in a sense, wet, though most of that water is frozen as hard as rock or drifting as vapor in the void. Liquid water, the elixir of life, is the rare prize, requiring just the right temperature and pressure, the delicate balance of the Goldilocks zone. But the ingredients are there, scattered across the cosmos, waiting for the right conditions to come together to create the warm, salty oceans where chemistry can become biology. The expansion of the universe is not just moving galaxies apart, it is stretching the wavelengths of light that travel through it. This cosmological redshift drains energy from photons as they travel. A photon of high-energy ultraviolet light emitted by a distant star might arrive at Earth as a low-energy infrared photon, having given up its energy to the expanding fabric of space. The universe is slowly cooling down, the fiery heat of the Big Bang dissipating into the growing volume of the cosmos. We are moving from a hot, dense past toward a cold, diffuse future, a one-way journey driven by the second law of thermodynamics. Entropy increases, order degrades into disorder, energy spreads out. This is the arrow of time, the reason we remember the past but not the future, the reason broken cups do not reassemble themselves. On the grandest scales, the universe is slowly winding down, spending its energy capital, moving toward a state of perfect equilibrium and stillness. But that end is so distant that it serves only as a horizon, not a destination. For now we live in the stelliferous era, the age of stars, a time of activity and light. New stars are being born right now in the Orion Nebula, in the Eagle Nebula, in galaxies millions of light years away. Planets are coalescing from dust, black holes are merging. Life is, at least on one planet, looking up and wondering. The universe is vibrant and dynamic. Even the empty spaces are rich with fields and potential. The vacuum seethes with virtual particles. Dark matter forms the scaffolding for visible light. Dark energy pushes the horizon outward. We are surrounded by a machinery of immense complexity and subtle beauty, a system that has produced consciousness capable of appreciating it. Think of the auroras on other worlds. Jupiter has auroras larger than the entire Earth, glowing in ultraviolet and X-rays, powered by the volcanic eruptions of its moon Io, which spews tons of sulfur and oxygen into Jupiter's magnetic field every second. Saturn has ghostly auroras that dance around its poles. Even brown dwarfs, those failed stars floating in the dark, have been observed with auroras, driven by weather patterns in their metallic atmospheres. These displays of light are the visible manifestation of invisible forces, magnetic field lines snapping and reconnecting, particles funneling down onto atmospheres, painting the poles of planets with the colors of excited atoms. It is a universal phenomenon, a reminder that magnetic fields are ubiquitous, protecting planets, guiding particles, shaping the environment of space. The concept of an orbit is a surrender to gravity. To orbit is to fall forever without hitting the ground. The International Space Station is falling toward Earth, pulled by gravity, but it is moving sideways so fast that the Earth curves away beneath it at the same rate it falls. It is a state of perpetual freefall, a delicate balance between velocity and gravity. The moon falls around the Earth falls around the sun falls around the galaxy. Everything is falling, caught in the gravitational embrace of something larger, a nested hierarchy of motion that keeps the universe from collapsing into a single point or flying apart into chaos. It is a smooth, silent gliding through the vacuum, a path traced by the curvature of space itself. As we drift towards sleep, we can imagine ourselves floating in this vastness, weightless and unburdened. The concerns of the day seem small when set against the backdrop of 100 billion galaxies. The rush of our lives slows down to match the pace of the stars. We are made of the same stuff as the nebulae and the novae, atoms forged in the dark and brought together for a brief moment to breathe and think and dream. We are the universe experiencing itself, and as we close our eyes, we return to the quiet darkness from which we came. A darkness not of emptiness, but of potential, of peace, of the deep, unending calm that holds the stars in their places and cradles the galaxies in the night. The rotation continues, the orbits hold steady. The expansion goes on, the universe breathes in its slow, rhythmic time, and we breathe with it, drifting on the tide of space-time, safe in the vast, beautiful, slumbering cosmos. Night. The rotation continues. Hold steady. The expansion goes on. The universe breathes in its, and we breathe with it, drift time, safe in the vast, beautiful, slumbering cosmos. Time, safe in the vast, beautiful, slumbering cosmos. Vast, beautiful, slumbering. Beautiful, slumbering.